conservative. Okay, if we can show that this vector field f is conservative, conservative means it can be expressed as a gradient of a scalar function. Okay, if we can, if the scalar function f exists such that the vector field f is equal to the gradient of f, okay, then we can evaluate this line integral of vector field f using the fundamental theorem of line integral here. Now, how to check whether a field is conservative or not? We have a test, isn't it? We have a test that I have shown you before. How to show that uh, uh, whether f is conservative. It needs to show what? F is conservative means you must satisfy this set of three equations. Yeah, it must satisfy this three equations here. If f is if the vector field f is conservative and j plus pk is conservative, that is, what is the equation? The set of three equations. Can anybody tell me? Yes? Okay, let's recall. Let's recall this idea of this line integrals of a fundamental theorem of line integral. The vector valued functions. Where did I discuss that? It's divergence and curl, isn't it? Divergence and curl. Yeah. You see this? Yeah. Yeah. You see this? This is what we have discussed before. The conservative field test. Okay. P partial y equal to n partial z. Okay. That this is the set of equations that we need to show that it satisfies. Where is that pen? Okay, that P partial y. Just a minute. I'm looking for my pen here. Yeah. Okay. It's P partial y equal to n partial z. M partial z equal to P partial x, and n partial x equal to m partial y. Yeah. Okay, so we need to show that P partial y equal to n partial z. Then m partial z equal to P partial x, and n partial x equal to m partial y. Yeah. So if f is conservative, that means it satisfies these equations. Then then there exists a potential function. Okay, then there exists a potential functions phi, or in this notation here f, such that the vector field f is equal to the gradient of the scalar f. Okay, yeah. So not all vector field f is conservative. I've shown you some examples where the vector field f is not conservative. That means it does not satisfy the set of three equations here. Then there is no f. Then it has no potential function. Okay. So this is what we have discussed. In this lecture notes, okay, we look at some examples of evaluation of vector field. Okay. Using the fundamental theorem of line integral. Yeah. So in this example, we do the conservative field test. So we showed that the vector field f is conservative. So then there exists, okay, a potential function phi. So the next step is to determine the potential function phi. And once it has been determined, then we can evaluate the given line integral of the vector field f using the line integral of of the fundamental theorem of line integral here. All right. And then this is an example for the two-dimensional case. However, it is shown here that m and n here does not satisfy the set of equations n partial x equal to m partial y. So we cannot apply the fundamental theorem of line integral. So we have to use the parametrization method, the old method, which is the parametrization method. Yeah. This is an extra example which I have provided to you after class. Yeah. In these notes, I've given extra example which is written after class. So this is to further enhance your understanding. So this is again a vector field. Given this vector field in 2D, in two-dimensional space, um, and gamma is a part of a parabola with initial point 0 and terminal point 4. Okay, so here I have solved it using two methods. One using the old method, which is the parametrization method, and we arrive at the value 128. The second method is by using the fundamental line of integral by first checking that whether f is conservative. So here we have shown that n partial x equal to m partial y. So vector field f is conservative. So there exists potential function phi such that f is equal to a gradient of phi. And the next step is to determine the potential function phi. And then once we have obtained the potential function phi, then we apply the fundamental theorem of line integral here. And we arrive at the same value using the old method. Yeah. So if you compare these two methods, method 2 is actually easier, right? Easier, yeah, because we don't need any parametrization. For the first case, we need to find the parametrization of the curve gamma. Yeah. But in the second case, we don't need to determine the parametrization method, the parametrization of the curve gamma, but we need to determine the potential function phi. And then I've also given you in this note another extra example. It's a sample final exam. We are given a vector field F as shown here. Show that it is conservative. Hence determine the potential of the vector field F. Hence determine the work done by this force field in moving an object from the point 1 minus 2, 1 to 3, 1, 4. You see, in this question here, no path is given, right? From the terminal, from the initial point to the terminal point, there is no description of the path involved. Yeah? There is no description of the path from the point, from the initial point to the end point. Okay, so no curve is described here. So this is an indication, when you have such question, this is an indication that the 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 fundamental theorem of line integral is must be applicable here. Okay, so we check to make sure, we check whether the given force field F is conservative. Okay, and here we have shown that it satisfies the set of three equations. So the force field F is conservative, hence there exists a potential function phi such that the vector field F is equal to the gradient of phi. Yeah? So we determine the gradient of phi by solving this set of three equations here, 1, 2, 3. Okay, and then finally we obtain the function phi equal to x squared y plus xz cubed plus c. Yeah. So now, having found phi, now we are in the position to apply the fundamental theorem of line integral. So the work done is phi at the end point minus phi at the initial point. And after substitution and simplifying, the result is 202 joules here. Okay. Any question for this example? I hope you have studied this example. Because this extra example was given to you after the class. Yeah, was written after class. Do you have any question on this example?
So far, so good, Doctor.
Okay, thank you. Below, I have given another extra example. Yeah. This is taken from a calculus book. This is an exercise, a problem from a calculus book by Ellis and Gulick. Assume that an electron is located at the origin. I have taken this example. It is related to electron. Okay, you are an electrical engineering students, so I thought this example might be suitable, for this group. So assume that an electron is located at the origin and has a charge of minus, time minus 1.6 times 10 to the minus 19 coulombs. Yeah. It is possible to have a negative charge, right, for an electron. Yeah. So find the work done by the electric field on a positive unit charge that moves from a distance of 10 to the minus 11 meters to a distance 10 to the minus 12 meters from the electron. Yeah, so that means the charge, the unit charge is moving closer, right, to the electron. There's a hint given here. The electric field is conservative. Yeah? Then, so recall this. Yeah, I have shown you when I first introduced you this concept of vector field. I've shown you an example. I've shown you examples of gravitational field, electric field also. Okay, so go back to your previous notes and look that I have written this, the electric field. written in this form. So here Q is equal to minus 1.6 times 10 to the minus 19. And there's a constant 4 pi epsilon naught. So in this problem, it says take 4 pi epsilon naught equal to 1.113 times 10 to the minus 10. Okay. Yeah. And it says here the electric field is conservative. So here is a M, N, and P of the given electric field. And then actually it can be shown that E is conservative. That means it satisfies the set of three equations. So I leave it to you, to verify this. Yeah. Hence there exists a potential function phi such that the vector field, electric field F is equal to, I'm sorry, there's a symbol here missing. I should have here the gradient of the potential function phi. Okay, and then it can be shown that the vector function, the potential function phi is given in this form. Again, I leave it to you to verify this. Yeah. So it is equal to this constants times 1 over square root of x squared plus y squared plus z squared. And this square root here measures the distance between the origin to the point x, y, z. Right? So if you look at the questions, you are given information on distances, right? Moves from a distance of 10 to the minus 11 meters to a distance of 10 to the minus 12 meter. So here is the distance formula here, the distance expression in the potential function phi. So by the fundamental theorem of line integral, so the work done W is equal to the phi at the end point minus phi at the initial point. So substitute the given values and simplify, and the result is 1293.8 joules here. All right. You have any question for this example? So here I have left out some details. I leave it to you to complete the details or verify the given results here. Okay. Any question for this example?
So
All right.
no,
If there's
Doctor.
no questions, so let's continue with our lecture. So today I'm going to discuss a Green's theorem here. I have mentioned a little bit about Green's theorem last week, but let me explain it a little bit more. Um, yeah, it is named after the British mathematician George Green, who lives in the around this 18th century here, 19th century here actually. Yeah. So before looking at the Green's theorem, let's recall something what we have discussed previous the fundamental theorem of calculus. Okay, the fundamental theorem of calculus. Suppose there's a capital F here that exists. Okay, assuming F exists such that the capital F prime is equal to f of x. You see, the integrand here is f of x. Okay, suppose f x exists such that capital F prime equal to f of x, or f of x equal to capital F prime. Yeah. Then by the fundamental theorem of calculus, this integral is equal to the antiderivative evaluated at the end point of the interval b minus the antiderivative evaluated at the initial point of the interval. Okay, so you have studied this. So Generally, it means it involves the interior interval and its endpoints. Okay, the integral is from over the interval a to b. But if the antiderivative of the integrand is known, then it is simply equal to the antiderivative evaluated at the endpoint b of the interval minus the endpoint minus the value of the antiderivative evaluated at the initial point of the interval, which is a here. And then we have seen the extension of this fundamental theorem of calculus to the fundamental theorem of line integral, which I have discussed with you earlier. Okay, so we have a line integral here of a vector field f dot dr. R is the position vector of the curve gamma here. So if okay, if phi exists, okay, if phi exists, if the scalar function phi exists, such that the vector field f is equal to the gradient of phi. Yeah, and remember the gradient of phi is a vector field. Yeah. Mm. Then the line integral is equal to phi at the terminal point minus the value of phi at the initial point. Okay, this is an extension of the fundamental theorem of calculus. Instead of an interval in the uh, of a line, now we have a space curve. Okay, a space curve. So the role of line interval here is now replaced by a space curve. Yeah, space curve with initial point and terminal point here, right? So there's a connection between boundaries and what and curve. Okay, here we have a connection between boundaries and interval, and in the fundamental theorem of integral, we have a connection between the initial terminal points with the boundaries of the curve. Okay, boundaries of a curve. There is another extension of the earlier two results called the Green's theorem. Yeah. So let's see what's the Green's theorem is. Suppose we have a region omega here with a boundary gamma, and gamma is in a counterclockwise direction here. Okay, we say that it is a counterclockwise. We say that it is positively oriented. Okay, we say in this case gamma is positively oriented. Yeah, it means that the region lies to the left when we traverse the curve gamma. Okay? It's positively oriented in the counterclockwise direction here is positively oriented. Yeah, the region lies to the left uh, of gamma when the curve gamma is traversed in the direction. Yeah. So suppose omega is a region in the xy plane bounded by a closed curve gamma. Okay, this applies to a region on a plane bounded by a closed curve gamma in the counterclockwise direction. Yeah? In the counterclockwise direction here. You should, I think the proper word here is direction. Yeah. Suppose F is a vector field mi plus nj. Okay, there is no vector k here because we are dealing with a two-dimensional space where m and n are continuous functions of x and y having continuous derivatives in omega. Then the vector field, then the line integral of the vector field f okay, which is also equivalent to this alternative form, is equal to the double integral of over this region omega here, where the integrand is n partial x minus m partial y dA. Okay, look at this line integral. We have a circle there, right? This is we use this notation if it is a line integral with closed curve. Okay, if if we use line integral to a closed curve, yeah, closed curve, and then in a counterclockwise direction. Okay, if gamma is a closed curve and counterclockwise direction, so we use this special form of line integral symbol here. Line integral, you see there's a circle here in the middle of the line integral symbol here. So that means we are dealing with gamma which is closed and in a counterclockwise direction, right? And this is only for a two-dimensional case. Yeah, this Green's theorem here is applies only for 2D case. Yeah. So this shows a connection between the boundary, okay, and the region. This result, this shows the connection between the region and the boundary. In the previous cases, we have a result that shows the boundaries and the interval. Okay, we have here the boundary is AB, the interval A to B. Here we have a space curve gamma with the boundaries, initial point and terminal point. So here we have a region omega with boundaries, boundary gamma here. All right. So this is give us another method for evaluation of double line integral of a vector field for two-dimensional case. Yeah. So the
The
proof is that yes, yes.
the x-axis and y-axis is
Oh,
yeah.
yeah, you're
Is
right.
it
I, yeah, you're right. It should be the y-axis here and the x-axis there. Okay, you're right.
uh
Somehow I've
thanks,
written it
doctor.
wrongly there. Yeah, thank you, thank you. Mm. Okay, so this is the correct label for the axis. Yeah. The proof is because this result has the status theorem, so that's a proof. Yeah, the proof is quite involved. So I'm not going to go through the proof. If you are a mathematics student, I will go through the proof. But I think let's for your case, let's see the application of this Green's theorem here.
And we
All right, so let's
represent the
see
boundary
some
conditions here
examples.
with this sort of notational shorthand we've got. And I'll explain this here in a second. All right, now this doesn't look exactly like the thing I just showed you, the actual mechanical thing. It doesn't look exactly like this, but it looks pretty close.
Suppose,
okay? What's
okay,
this thing
here's
mean
the
right
question.
here? This little triangle with the sort of comb-looking thing on the other
Suppose
side of
gamma
it
is a curve,
represents
is a closed curve. Yeah, to be more precise, it is a closed curve in the counterclockwise direction. In the shape of a triangle. In the shape of the triangle with vertices at 0, 0, 1, 0, 0, and 1, 0. Okay. Evaluate. Yeah. Evaluate this line integral. Here it is given in the form of the alternative form of the line integral. Okay. This is a line integral of a vector field in the alternative form. Yeah. Okay, let's first sketch the triangle. So the triangle is on the xy plane. The vertices, one vertex is at 0, 1. Another vertex is at the origin, 0, 0. And another vertex is what? 1, 0. Or 0, 1 is up here, actually, on the y-axis. This is 0, 1. Yeah? So we have this triangle with these three vertex.
Shouldn't the
Oh, I'm sorry.
x-axis
Yeah,
okay.
yeah, I know. Okay, thank you. This should be 1, 0 there, right? And it is set in the counterclockwise direction. So the arrow should be in the counterclockwise direction. So this is the curve gamma. Okay. So let's look at what are the methods that we have used for evaluation of these integrals. The old method, right? We have the old method. We have the theorem of the fundamental theorem of line integral method, and here is and then the Green's theorem. Yeah. So let's consider the old method, which is the parametrization method. Yeah. Suppose I want to solve it using the old method, which is the parametrization method. Okay. So that you have to split gamma here into three, gamma 1 plus gamma 2 plus gamma 3. Let's call this as gamma 1, gamma 2, gamma 3, right? The closed curve gamma can be viewed as a joint of three separate curves, gamma 1, gamma 2, gamma 3. So if I were to apply the old method, then I have to split this integral into 3. And you need to determine the parameterizations of gamma 1, gamma 2, gamma 3. So there's a lot of work, isn't it? Yeah. We need to determine the parameterizations of gamma 1, gamma 2, gamma 3. So it's a lot of work, right? This is a lot of work. Yeah. So let's consider. Let's see if the fundamental theorem is it applicable? Is the fundamental theorem of line integral applicable? If it is applicable, the answer should be 0, right? Because it is a closed curve. So how to determine whether it is applicable? From the given integral, we know that this is m and this is n, right? Yeah. So we do what is called the testing, the conservative test. What what is it that we want to? So here m is equal to x squared plus y squared, and here n is x plus 2. We use the conservative field test. Is what is m partial y? M partial y here is 2y. Now, is it equal to n partial x? That is the conservative field test for a vector field in two-dimensional space. And n partial x is equal to 1, right? So they're not equal. So the answer is no here. They're not equal. So therefore, the fundamental theorem of line integral is not applicable. Yeah, for the evaluation of this line integral here. This. Okay, so let's take a look at the Green's theorem. Okay, can we apply the Green's theorem? Because it is a closed curve, right? And it is also, so the closed curve is a boundary of the region gamma omega here, right? Yeah, the closed curve gamma is a boundary of the triangular region omega there, isn't it? So by the Green's theorem, by the Green's theorem, the curve, the line integral of what just now, of x squared plus y squared dx plus x plus 2 dy is equal to the integral, the double integral over the region omega of n partial x minus m partial y dA. Okay, by the Green's theorem. So we have m and n here. So m refers to x squared plus y squared, the coefficient of dx, and n refers to x plus 2, the coefficient of dy. So the n partial x is what? It's 1, right? And m partial y is 2y. So the line integral reduces to this double integral. And we have studied evaluation of double integral before. So now we try to evaluate this double integral. Now to evaluate this double integral, we must know the limits, isn't it? What are the limits for this double integral? So go back to the region omega here. What are the limits for x and y? Yes?
The limit of y is minus
Yes.
x plus 1 until 0. 0
Uh-huh.
to minus x plus 1. And then for
Yeah.
x is 1 to 0.
Yeah, the equation of this line joining 1 0 0 1 is x plus y equal to 1, right? So that means y equal to 1 minus x. So for the region omega, it consists of all points x, y, such that x is between 0 and 1, and y is between 0 up to that that line, 1 minus x. Okay, so that means we must integrate with respect to y first. Okay, so we integrate this with respect to y first, because y is bounded by functions. So y is between 0 up to 1 minus x, and x is between 0 and 1. So we integrate first with respect to y. So the result is y minus y squared. Y is between 0 up to 1 minus x dx. Okay, so we substitute y with the upper limit 1 minus x. When y is 0, it's 0. So now it reduces to this integral, a single integral here with respect to x. So before we do the integration, we simplify the integrand. 1 minus x squared is 1 minus 2x plus x squared dx. So what is that? 1 cancel out. We have minus x plus 2x is x. Then we have minus x squared, yeah? Minus x squared dx. Okay, so that is a simple integral. So I leave it to you to show that the value is equal to 1 over 6, yeah? Right? So in this example, it is a lot easier to apply the Green's theorem, yeah, for its evaluation. If we were to apply the fundamental theorem of line integral is not applicable. The old method, the parameterization method, involves too much work here. So the best way is to use the Green's theorem here. Any question?
Sir, so does that mean
Yes.
we have to find the fundamental theorem first, or we just have to agak-agak to use the Green theorem?
Yeah. Um, mm, if the you see the question here does not say which method to apply, right? It doesn't say which method to apply. Yeah. So we have the old method. Yeah. So I mean, there's a decision making here. There's a decision making process here. You can think, because this is a closed region. For in the first place, it's a closed region, right? Yeah. So something that bring this Green's theorem to mind, actually. Yeah. You can have a mental, think. You can think this mentally that if I were to solve this using parameterization method, you can. This involves parameterization of gamma 1, gamma 2, gamma 3. Okay. And also a quick check of this conservative field test shows that it is not, FTLI is not applicable. Yeah. So then you can quickly uh, make a decision that I then should apply the Green's theorem here. Okay. In
Doctor,
some questions, they ask you to use Green's theorem. Sometimes it is all written in the question, apply the Green's theorem. Then there's no need to think about FTLI or the parameterization method. Yeah. Yes.
so can I when I see the question, the gamma is in a closed loop, so I can strictly go to use Green theorems, is it?
Yeah, you should think it is that Green's theorem is applicable, but sometimes the FTLI is also applicable, right? Sometimes FTLI is also applicable, and because this is a closed curve, you should immediately conclude that it is equal to 0.
Yeah. That's
Yeah. So then no need to use the Green's theorem. Yeah. If you use the Green's theorem, you will also end up with 0. Okay, if the fundamental theorem, if the FTLI is applicable, then we know that because it is a closed curve, so it is equal to 0. Yeah. If it is, then to me, then there is no need to use the Green's theorem.
I see. Thank you,
Remember the
Norif.
fundamental, yeah. Here, you see our discussion on the fundamental theorem of line integral. If f is conservative, right? The vector field f is conservative, and gamma is a closed curve, we can immediately conclude that it is equal to 0. Yeah, so then we don't have to use Green's theorem. But if the question asks you to apply Green's theorem, then you must apply Green's theorem. Yeah. Okay, let's look at another example. Okay, this is another example here. Suppose that I think this is in the exercise problem. Let me check. Let's try one more example. Suppose let f be the vector field m 2y cube I plus x to the power of 4 plus 6 y squared xj, and the curve C is as shown below here. This is the y-axis, the x-axis. We have a closed curve like this. This is 0, 1, 1. And the curve here is x to the power of 4 plus y to the power of 4 equal to 1. So we want to evaluate this this line integral f dot dr. Yeah. Okay, so again, this is a closed curve, right? C here is a closed curve, yeah, a counterclockwise direction. And if you were to apply the parametrization method, it takes a lot of work because you have to split this line integral into 3, one over each what curve segment here, C1, C2, C3. Okay, Um, what about, wait a minute, what happened here? I got no power. There's no power. Mm, okay. All right. So let's apply. What do you think? Is FTLI applicable? Maybe it is applicable. So let's do a quick check. Here m is 2y cubed, and then n is equal to x to the power of 4 plus 6y squared x, isn't it? So what do we do? So what is the conservative field test? Remember what we in the previous example is m partial y equal to n partial x. So m partial y is equal to 6y squared. Is it equal to n partial x, which is 6y squared also, isn't it? M partial y is 6y squared, and n partial x is also 6y squared. It is equal, right?
Doctor, so is it the differential of x to the power of 4 is different?
Yeah, I'm sorry. There should be 4x cubed as well, isn't it?
Yeah.
Yeah, it should be 4x cubed plus what? 6y squared. So clearly it's not equal, right? Not equal, yeah. Not equal. So therefore FTLI is not applicable. So let's consider Green's theorem. Okay. So by the Green's theorem is equal to the double integral of the region containing bounded by the closed curve C. Yeah. And then what? N. What is the in this integral here? What is the integrand? N partial x minus m partial y. Right? The integrand is n partial x minus m partial y. Yeah. And here n partial x is 4x cubed plus 6y squared minus m partial y, which is 6y squared. So 6y squared they cancel out. So we have this double integral of 4x cubed dA. Okay. So what are the limits for this double integral? We have to go back to the diagram. This equation implies y equal to 1 minus x to the power of 4 to the power of 1 over 4. And x is between 0 and 1, right? X here is between 0 and 1. So again, we have to differentiate this with respect to y first. dy dx, y is from 0 up to 1 minus x to the power of 4, 1 over 4, and x is between 0 and 1. Okay? Can you evaluate this double integral yourself? Can I leave it to you to evaluate this double integral yourself? Okay? So we integrate this with respect to y first, right? With respect to y first. So we get x cubed y, yeah, for the integral to 1, x cubed y. So y is from 0 up to 1 minus x to the power of 4 to the power of 1 over 4, yeah, dx. So we do the substitution for y, then we get 1 minus x to the power of 4, 1 to the power of 1 over 4 dx, right? When y is 0, it's 0. Any idea how to evaluate this, the integral? Any idea?
Use substitution.
Uh-huh. What substitution?
U equals to 1 minus negative 8. Yeah, 4 to the power of 4.
Okay.
4.
Yes.
X to the power of 4.
Yes. So du is minus 4x cubed dx, right? Yeah. So we have 4. 1 minus x to the power of 4 is u. And x cubed dx is du over minus 4. What about the integrand? When x is 0, u equal to 1. When x equal to 1, u is 0. Okay. So first we see that 4 cancel out. And then because of the presence of the negative sign here, that means we can interchange the limits 0 to 1. Yeah. So I leave it to you to show that the answer is 4 over 5. Yeah. So here we also have a line integral which can be evaluated using a Green's theorem here. And of course, this is much better than using the parametrization method. Yeah. Any question for this example?
No, doctor.
No. Okay, let's do another example then. Okay, your final exam will certainly have some questions regarding Green's theorem. All right, so let's look at one more example. Suppose m is equal to x minus x squared y and n is equal to x cubed and c or gamma is the circle x squared plus y squared equal to 4 in the positive orientation here. Evaluate this line integral m dx plus n dy. Okay, so again, this is this is a line integral in two-dimensional space, and the curve is gamma. It's a closed curve. This is a closed curve centered at 0 of what? Centered at 0 of radius 2. Okay, here it is 2 here. And it is in a counterclockwise direction. Okay, so let's apply the Green's theorem. The one method is the parametrization method, right? One method is the parametrization method. Then you need to parametrize the circle. And then is FTLI applicable? Is FTLI applicable?
No.
No, right? Okay,
Yeah.
you can check that quickly, that FTLI is not applicable. So by the Green's theorem, this line integral here, m dx plus n dy is equal to double integral. Let's call R as the region bounded by this circle. And the integrand is n partial x minus m partial y dA. Yeah. And n partial x is 3x squared. M partial y is minus x squared. Minus x squared. So that is 4, right? 4x squared. So let's pull out the constant 4. Then we have x squared dA. Yes. Any suggestion how to evaluate this double integral? You need to find
Use
the
polar.
limits.
Can you use
Yes,
polar?
yes. Okay, because the region R is circle, so the best way is to use the polar coordinate. Yeah. So we don't have to use the Cartesian coordinate all the time, depending on the given region R. So you see R here, in terms of polar coordinate, R is between 0 up to 2, which is the radius. 2 is the radius of the circle, and theta is, because it's a complete circle, so 0 is theta 2 pi, okay? So this region R has point R theta, okay? So you can see here, R is from 0 to the circle. R is bounded between the 0 and circle, right? The radius of the circle is 2, and theta is from 0 up to 2 pi. So that means in terms of polar coordinate, we replace x by r cos theta. What about dA? Remember, dA becomes what?
D theta. dr d
R
theta.
dr d theta. Yes. So the inner the order is dr d theta. So that means the inner integral is with respect to r. R is between 0 up to 2, and theta is from 0 up to 2 pi. Okay. So we have 4, the integral 0 to 2 pi, the integral 0 up to 2. That simplifies to what? Look at this integrand here. We have r squared times r, which is r cubed, and we have cosine squared theta. So we can write this as a product of two single integral, right? Because the limits are all numbers, And the integrand is a function of r alone times a function of theta alone. So we can evaluate this as a product of two single integrals. The integral with respect to r, which is r cubed dr, times the integral with respect to theta, which here it is cosine squared theta d theta. Alright? The integral with respect to r cubed, it is what? The integrand is 1 over 4 r to the power of 4, 0 up to 2, right? So this is equal to 16 over 4 is 4, right? 16 over 4 is 4. What about the second? How to evaluate the second integral? First, we change cosine squared theta to what? Remember, we have this identity. Important for you to remember, some trigonometric identities. Okay. So therefore, cosine squared theta is equal to cosine 2 theta plus 1 over 2. And therefore, the integral is equal to what? 1/2 the integral of cosine 2 theta is sine 2 theta over 2. The integral of 1 is theta, right? Theta is from 0 up to 2 pi. Okay, I leave it to you to show that it is equal to 16 pi. Okay, after simplification, the result is equal to 16 pi. Okay, so in this case, we use a Green's theorem with polar coordinates. Okay, yeah, with polar coordinates. So it depends. So we have to look at the given region. Yeah, you have to look at the given region. Any question for this example? Let's look at another example. Yes. Consider, evaluate the line integral here. X over y dx minus y over x dy, where c where C is as shown. Okay, below here. So we have the x-axis, the y-axis, and in this case, C is a rectangular boundary. It is 1, -1, 1, and -1. Again, it is in a counterclockwise direction, C. What do you think? Okay, the old method is a parametrization method here, right? But that takes a lot of work, isn't it? You have to split C into a join of four curves, C1, C2, C3, C4. Let's look at the other possibilities. Is FTLI applicable? Yes. Is FTLI applicable?
No.
Do the what? The conservative test, isn't it?
Yeah.
You can do the conservative test. Yes. So here m is equal to x over y. N is equal to minus, yeah, not because of a minus sign there. So n is minus y over x. So we look at m partial y. What is m partial y? It's minus x over y squared. Is it equal to n partial x? N partial x is plus, isn't it? It's plus y over x squared. So it is not applicable. It is not equal. So FTLI is not applicable. Not applicable here. What about Green's theorem? Can we apply Green's theorem?
Yes, you can.
Actually, the answer is no. Look at the statement of Green's theorem again. Here. There's a condition on m and n here, where m and n are continuous functions of x and y having continuous derivatives in omega. Okay? You should pay attention to the conditions m and n here. M and n are continuous functions of x and y and having continuous derivatives in omega. So this condition is actually important before one apply the Green's theorem. Okay, it is important to check that these conditions for m and n are satisfied before applying the Green's theorem. So I did not do that because previously because it is applicable. All this why it is applicable. Yeah. See here. Let's go back to the very first example. Yeah, you see, m and n here are continuous, right? In the region omega, and the partial derivatives are also all continuous, all well defined, isn't it? See, n partial x is you see this integrand here is continuous in omega. Yeah. And here in this example also, when we apply the Green's theorem, okay, 4x cubed is also continuous, right? It's also well defined in the region R here. It's continuous in the region R. Here also, okay, n partial x minus n partial y, you see, they are also continuous. Partial derivatives are also continuous in the circular region R here. This is no longer the case for this example. Okay, they are not continuous. Yeah. Not continuous inside the region, say R here. Not continuous inside R because it is undefined at 0. Undefined at 0, right? They are undefined at 0, 0. Yeah, the function mn it's not continuous there. So in this case, it is not applicable. Yeah, because this condition is not satisfied. Because this condition here is not satisfied. Okay, because the following conditions are not satisfied. Yeah. Not only m and n must be continuous, they should have continuous partial derivatives as well in the region omega here. So what does it mean? It means we have to fall back to the old method. We have to fall back to the old method. FTLI is not applicable. The Green's theorem is also not applicable. So we have to resort to the old method, which is the parametrization method. Even though parametrization method involves a lot of work, but we have to do with it. Yeah, we have to do with it. Because we have seen here the FTLI is not applicable, the Green's theorem is not applicable. So the only thing left is the old method, which is the parametrization method. Yeah. Okay. Even though it is complicated, we need to use we need to split the integral into C1, C2, C3. Yeah. Even though it involves a lot of work, but there's the only choice left. Yeah. But I'm not going to solve this. Yeah, because I just want to show it to you that in some cases, this thing can happen. Yeah, some cases this thing can happen. Yeah. Any question? Do you have any question?
No, okay.
Okay. I will upload this into the e-learning, this notes, so that you can, study it and, and try to understand what's being discussed here. Okay, before I end this lecture, I want to show you an interesting application of Green's theorem related to area. Yes. How this Green's theorem can also be applied to find area bounded by a closed curve. Suppose we have a closed curve gamma here, gamma, which in a counterclockwise direction. And then suppose the region bounded by the closed curve gamma is omega here. Now, we know from our double integral study that the area of omega is a double integral of 1 dA, right? Over the region omega. Yeah. So this is for a two-dimensional case. Now, suppose we can choose m and n such that n partial x minus m partial y is equal to 1 here. Then by the Green's theorem, okay, if I can choose n and m such that this 1 can be written as n partial x minus m partial y, then by the Green's theorem, this double integral is equal to the line integral m dx plus n dy. Okay, and here are some choices of m and n to 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 make it works, that n partial x minus m partial y equal to 1. If I choose m equal to 0, n equal to x, then m partial y equal to 0, n partial x equal to 1. Therefore, we have here where is it? Yeah. Therefore, this implies what? N partial x minus m partial y equal to 1. Another choice is m equal to minus y and n equal to 0. So m partial y is minus 1, n partial x is equal to 0. And again, we have n partial x minus m partial y equal to 1. Another choice is m equal to minus half y, n equal to half x. Okay, so m partial y is minus a half, and n partial x equal to a half. So this also implies that n partial x minus m partial y equal to 1. So there are many ways of choosing m and n, so that n partial x minus m partial y equal to 1. Okay, the first choice shows that the area is equal to the line integral x dy. The second choice implies that the area is equal to minus the line integral of y dx. The third choice leads to the formula a equal to 1/2 x dy minus y dx. Yeah. Uh, so all these area formulas are applicable here to evaluate the area and for the region bounded by the closed curve gamma. But the third formula here is more often used, because it has certain amount of symmetry here. Okay, let's look at an example. Suppose I want to find the area. Determine the area bounded by the ellipse x squared over a squared plus y squared over b squared equal to 1 using a Green's theorem. Okay, using Green's theorem. So we have an ellipse here. Suppose this is just a sketch. It doesn't have to be accurate. It's A, B, and then here is Y, X, right? What is the area? Remember the area of an ellipse? What is the area? It's already known, right? It is known that what? The area is pi AB, is it? Pi AB unit squared. Okay. Using double integral, using the parametrization method, yeah. It is already known that the area of an ellipse is pi AB unit squared. So let's use the Green's formula, area formula. By Green's theorem, the area, let's denote the region here as R, 1 dA is equal to, this is the curve gamma of what? 1/2. Let's use the third formula. The third formula is, what is the third formula? X dy minus y dx. Okay, y dx. Yes. So this curve gamma has the parametrization xt yt equal to a cosine b, yt equal to cosine theta or t, and yt is equal to b sine t, right? Where t is from 0 up to 2 pi. Yeah. So by the line integral, remember how to evaluate line integral in this alternative form? We replace x by xt, replace y by y prime t, replace y by yt, we replace dx by x prime t, everything multiplied by dt, and t is from 0 up to 2 pi. Yeah. So let's substitute. Xt is a cosine t, y prime t is b cosine t, yt is b sine t, x prime t is minus a sine t dt. Okay, so simplify the integrand, we get ab cosine squared t, minus and minus we have plus, and we have again ab sine squared t dt. Okay, we can pull out the common factor AB here. So we get AB over 2, the integral 0 up to 2 pi. Then we have cosine squared plus sine squared, which is 1. And that integral is 2 pi. So finally, the answer is AB pi. Okay, AB pi. That's what we have already known. Okay, so this is another interesting application of Green's theorem for finding area under a curve. And there is a device, there is a device called planimeter. How to, let me show you. Have you heard of this device called planimeter? Planimeter. Planimeter. Yeah, you see? It's a device called planimeter. Essentially, to calculate the area bounded by a region, bounded by a certain curve. So the principle behind it is the Green's theorem. Yeah? There's a device. Where is it? This is from Wikipedia. Yeah, you see here, the idea behind it is this. Is the Green's theorem here. It's a planimeter. It's the mathematical derivation. They have a device such that the device traces the boundary of the curve, and then they tell you what is the area bounded by this region, about of the area of the region bounded by this closed curve. Yeah. So the principle behind it is this the Green's theorem here. Green's theorem here. Okay, I leave it to you to Google this and read this on your own. So the device is known as called a planimeter here. Yeah? Okay, enough for today. So tomorrow we have another class tomorrow. So tomorrow I will start talking about the surface integral. Yeah? I will talk about surface integral. Where is it? Yeah, if you look at the cost information, so I've already covered Green's theorem. I've already covered Green's theorem here. Yeah. So tomorrow I will start talking about surface integrals and Stokes theorem. And the next week we will talk about the last topic for this course called Gauss divergence theorem. Okay. Stokes theorem is related to double integral, while Gauss divergence theorem is related to triple integrals over a solid region. Yeah. Okay, so enough for today. So before we end this meeting, let me show you the what? The where is it? Where is it? Oh, I need to log in. I need to log in to show you the QR code. Okay, here is the QR code for your attendance, so please scan it. Thank you for attending this online class. You may leave this after you have finished scanning this QR code for your attendance.
Thank you very much, Doctor.
Thank you.
Thank you very much, Doctor.
Thank you.
Hey, Doctor. Bye.
Thank you.
Doctor,
Yes.
can I have a request for you?
What is it?
Since today we'll be having a test and tomorrow we also will have a test, and Thursday we